Thanks, Peter. And what I'm talking about today is joint work with my student, Jack Alsop. In Canada and Australia and many other places, we've had to deal not only with COVID, but also with some devastating fires. And our eucalypt trees have a remarkable ability. Oftentimes they can be burnt to a stump, but still manage to send forth new growth afterwards. And I sort of feel like this is where we're at in terms of in-person conferences, where we're just in the first tentative stages of sprouting forth and trying to regrow. So there's two things in my title. I'll introduce what the cast of this particular story is. Of course, you've already seen a lot of this, so we know what a one factor is. It's another name for perfect matching. One factorizations we've also seen. Here's a one factorization. That's not the one factorization I'm talking about. One factorization is, of course, the decomposition into one factors. So I make my graph out of glass, and then I carelessly drop it, and it shatters everywhere. And I didn't even use safety glass, so I get lots of sharp edges. In fact, I get only edges, and then I sweep them up into little piles, and each pile is a one factor. So here I've done that with K8. And then you might want to try and put Humpty Dumpty back together again. So you can take two of your one factors, say these ones, and put them together and see what you get. In this case, when I put those two one factors together, I get a Hamilton cycle. That doesn't always happen, of course. If I take these two and put them together, then I get two C4s, so I get a disconnected two factor. So this leads to the idea of a perfect one factorization, which we have already seen today. And the perfect one factorization is one where you always get this situation, you never get this situation. So whichever two one factors you choose, when you put them together, you'll get a Hamilton cycle. That's, I'll abbreviate that P1F. And this has been done for many graphs, but today I'll only be talking about complete graph and the complete bipartite graph. Easy necessary conditions are for a perfect one factorization to exist. In Kn, n must be even. In Kn, n must be either 2 or odd. And I'll assume those conditions are holding throughout today's talk. Here's a K5, make it out of glass, throw it on the floor, get 5 one factors, and then I can try reassembling them, take these two together, and I get a Hamilton cycle. In fact, that happens for every pair of one factors here, which I'll leave you to check. So this is our first example of a perfect one factorization. So that was one of the things in my title. The other thing was something about Latin squares. So I'll tell you about that. So Latin square is just a square matrix where each row and column is a permutation of the same set of symbols. Today, my symbols will be 0 up to n-1. And I can look at two rows of a Latin square, say these two here, and that will define a permutation that maps the first row to the second row. In this particular case, it will map 2 to 5, 5 to 4, 4 to 2, and I call that a row cycle. So this is a really important concept for today's talk. In those two rows, of course, there are two other row cycles. I have a cycle on 0 and 3 and a cycle on 1 and 6. So those are the row cycles that I get from those two rows. In this case, I get 3 separate row cycles. And you could ask, you might hope that, in fact, the thing doesn't split up like this, that you get only a single cycle. So if I got a single cycle of length 7, and I got that for every pair of rows, it didn't happen here. It's a lot to ask, but it could happen. Then what I would have is something called the row Hamiltonian Latin square. So that means for every pair of rows, the permutation mapping one of those rows to the other is a single cycle. You can also play this game for columns. You can pick 2 columns and look at the permutation mapping those together. And you can also do it for symbols. And there are corresponding notions of Hamiltonicity for these things. In fact, these 3 notions of Hamiltonicity are related by an idea called conjugacy, which I will mention in a few slides. But those are the 2 objects that I want to talk about today, except they're really only one. So I can take a Latin square, I can make a graph out of it by choosing vertices for the columns another set of vertices for the symbols, and then each entry in the Latin square will give me an edge because it's pairing a column with a symbol. And I can work across the rows here and I can put in the edges that I get from that first row. I will necessarily get a 1 factor. I can do it for another row. I'll get another 1 factor. I can think, well, did that give me a Hamilton cycle or not? In this case, it did. And so I can do this for all of the entries in the Latin square. Of course, I will get a KNN when I do this. And so the Latin square is somehow encoding a 1 factorization of KNN in this way. And more particularly, the row Hamiltonian Latin squares will correspond to the perfect 1 factorizations of KNN. So these two objects which I've defined for you are really the same thing combinatorially. Okay, so that's what I'm talking about today. And we did already have mention of a little bit of the history in Mateja's talk. So this subject was all started by Kotzig, the Slovak mathematician Anton Kotzig in the 60s, who wrote several papers. He didn't actually fill in all of the details. He left some of those details to be sorted out later, but we can credit him with 3 important contributions. The first thing is that he knew how to build some of these things. He had 2 infinite families, one which works for orders which are 1 more than an odd prime, and the other which works for orders which are twice a prime. And so those are quite sparse families, but they are infinite. And he conjectured that these things actually exist all the time. So whenever n is even, you should be able to do this. And he also realized that there's a connection between perfect 1 factorizations of complete graphs and those of complete bipartite graphs. So these are the 3 things that Kotzig really did to start the subject off. Actually, there's some subtleties with this last theorem. It's not a 1-to-1 relationship, and it's actually a little bit more complicated than that. And I refer you to a paper I wrote with Ed Ihrig in 2005 if you want the full details of quite what the relationship is here. But nevertheless, we can go from complete graphs to complete bipartite graphs. And so that was sort of the start of the journey in terms of what Kotzig did. How far have we got in terms of proving his conjecture? Well, basically nowhere. So there's only, in all that time, we've found 1 other infinite family of perfect 1 factorizations of complete graphs, and they didn't give us any new orders. They all are for orders prime plus 1, but they're non-isomorphic to the Kotzig family. And that's as far as we've got in terms of general constructions. For the complete bipartite case, we know a little bit more. We have 7 infinite families. 6 of them come from this theorem and these other families that we know. And there's 1 extra. This one here can't be obtained using that theorem. So it shows the theorem is not reversible. And that's basically all we know. Well, except I'm going to tell you the 8th family today. So I'll give you another family today, but these families are hard to find. This is the point. Okay. So let's have a look at some numbers. So this is a game we've been playing for more than a century, but we haven't got very far. There's most recent progress is this number here, the number of perfect 1 factorizations of K16, which is computed in 2 independent papers. There's a bit of a story behind that, which you can ask me about at coffee. But that's not much progress considering how long we've been thinking about these things. The other thing I want to point out is how rare these perfect 1 factorizations are. Okay, you can see how many 1 factorizations there are, how few of them are perfect. It's a very rare, special, and I think quite beautiful property. That's something to bear in mind. Same sort of table for the bipartite case. Again, very rare duals, but maybe increasing numbers, maybe they always exist, who knows. Okay, and we've actually been doing this for longer, so since the mid-19th century, counting 1 factorizations of complete bipartite graphs. Up to isomorphism, these numbers are. Okay, so we don't know many infinite families. We do know a few sporadic orders, and actually the reason I chose to talk about this subject is it's obviously very dear to the heart of the birthday boy. He wrote quite a few papers actually on the theory, but also found 3 of these, or 4 of these small orders. No, a lot more than 4. He wrote 3 papers anyway on finding small orders of these things. The smallest unresolved case of Kotzig conjecture is now 64 as a result of these papers, which is pretty small considering we can actually find examples up to 22 million, but we can't ever see how to generalize them, and we don't really know what we're doing. So we're kind of stumbling around in the dark. It's a bit frustrating, but that's what we know in terms of complete factorizations of complete graphs that are perfect. Now I promised to tell you about conjugacy, so I should do that next. You can write a Latin square as a set of triples where you have the row, the column, and then the symbol that occurs in that cell. You can then take those n-squared triples, uniformly permute them, and reinterpret it as another Latin square. And this gives you 6 conjugate Latin squares. And if you do this, row cycles become column cycles, become symbol cycles. And so these things are really the same, same object combinatorially. And I'm interested in this parameter. Nu of L will be the number of conjugates. So there are 6 conjugates. How many of them are row Hamiltonian? Okay, it's not too hard to see that the answer should be even. And the reason is you can think about your bipartite graph. If you flip it upside down, so if you exchange columns and symbols, it won't change whether the factorization is perfect. So that's where you get the factor of 2 from. And that means that nu will always be 0, 2, 4, or 6. It's trivial to achieve 0. In fact, in a very strong sense, almost all Latin squares achieve that. That's not very interesting. We're interested, of course, in the cases when nu is positive. And it turns out that all of the previously known families had nu either 2 or 6. In fact, this is forced if you get your square from Kotzig's construction. But it also happens to hold for the squares that we have that weren't from that construction. So the nu equals 6 case is particularly interesting. It's particularly nice. We have a name for that. They're called atomic Latin squares. And we know a little bit about those. We can find 5 infinite families here. The most obvious is the Cayley tables of the cyclic groups of prime order, which are the atoms of group theory. And we can build some others of prime order as well, which are not isomorphic, and a few sporadic orders, which are prime powers. But as with many things in combinatorics, it's an open question whether you can achieve this property for orders that are not a prime power. So we know a little bit, not as much as we like. We know a little bit about nu equals 6, but there's this obvious gap of what about nu equals 4? Is it possible to have a Latin square where the row cycles are Hamiltonian, the column cycles are Hamiltonian, but the symbol cycles are not? That's basically the question I'm asking. So the previous infinite families didn't achieve this. And what I want to show you today is an infinite family that does. So it's going to use something called a quadratic orthomorphism, which I don't have time to define, but if you know what they are, that will help. I'm going to go straight to the construction. I will need, for this construction to work, I'll need my order to be a prime, which is 1 or 3 mod 8. And it will use the set of quadratic residues modulo that prime. And I define my Latin square like this. So basically, I have 2 different rules. The ijth entry is defined one way if j minus I is a quadratic residue, and another way if it's not. And this is how I build my Latin square. This Latin square will be called LP, and it will turn out to be the square that achieves the property that I want. Now, I've known for a long time that it achieves this property. We worked on it with, being me and some colleagues who I won't name because we weren't successful, worked on it for quite a while, trying to prove this thing it had the property, and then published the conjecture because we couldn't prove it. And then last year, I had an undergraduate project student, and we don't expect them to do anything original. We just give them something fun to play with. And so I gave Jack this problem just to explore, and lo and behold, blow me down, he actually found a way to solve this conjecture. So I will tell you about that. So his key insight was to find this old theorem by Beck, which allowed us to recast the problem in a way that made it more accessible. So in this slide, I will restrict just to the P equals 3 mod 8 case. And Fireby will be telling me what the permutation in that first row of the Latin square. And then you can write the map from the top row to the next row of LP as the product of these two P cycles. And I write it in this way because it's exactly the form that is required to apply Beck's theorem, which I'll tell you in a minute. But before I do that, I need to define this thing called the link relation matrix, which is what Beck's theorem is cast in terms of. It's a symmetric 0-1 matrix, which relies on comparisons between the entries that you see when you write your permutation here. And it's a P-1 by P-1 matrix, so indexed by the non-zero entries of ZP. And his theorem says that this permutation that I'm interested in, the permutation at the top of the slide, is an n cycle if and only if this link relation matrix is non-singular. So we've taken this question, which is quite a tricky number theory question, and we've made it linear algebra, and that seems like progress, right? Actually, Beck's theorem is way more general than this, but this is what we need from his theorem for our purpose. This is what we do when P is 3 mod 8. In the 3 mod 8 case, the orthomorphism group of my Latin square has a single orbit on unordered pairs of rows. So it's enough just to show this pair of rows is Hamiltonian, and it will follow that every pair of rows is Hamiltonian, which is fabulous. In the 1 mod 8 case, there are 2 orbits. So we need to actually do this sort of thing 3 times. And the details are annoyingly a little bit different, but they're basically the same. So we'll use this theorem 3 times. And so basically, we just have to show that this matrix is non-singular. And that's the challenge. Now, I'm not going to show you the details of it. It's about a 10-page argument. I'm going to try and give you a very quick flavor of how it goes using this example of P is 11. So this is the matrix we start with. Our job is to show that it's non-singular. And it has some very nice structure if you stare at it. If you have 2 consecutive residues, then those rows differ in exactly 1 column. If you have 2 consecutive non-residues, then those rows will differ in 2 columns, being the 2 columns with the same indexes as these rows. And starting with that observation, we are able to reduce our matrix in 3 phases. The first phase, we take 2 consecutive non-residues, and we look at those 2 rows and those 2 columns and realize that if we delete them, we won't change the determinant. So we zap those and we have a smaller matrix. There are no longer any consecutive non-residues, so that's the end of phase 1. Phase 2, I take 2 consecutive residues. They differ in exactly 1 column, which will be a non-residue. I want to get rid of that non-residue, so I'll get rid of that non-residue and one of the pairs of rows that I got, and I can show that deleting these 2 preserves the determinant, so I'll get rid of those. I can now do that again. 1 and 3 are not consecutive originally, but they're adjacent now, so I play the same game with them. I want to get rid of the non-residue 6, and I do that by getting rid of 3 and 6, and I get down to this. That's the end of phase 2. I've got rid of all of the non-residues except -1, which I want to keep. And so I now look at 1 and whatever's next, which will be a residue, and I use it to get rid of whatever was next, but not using 1 because I want to keep 1. I get rid of these 2, and I'll get down to the thing that's indexed by 1 and -1, which will always be this matrix, which is conspicuously non-singular. And I preserve the determinant all the way, so I know that my original matrix was non-singular. That's kind of the flavor of how we showed this thing is non-singular. Lots of details omitted. Now, the square that I've built for you has a nice property that it's isomorphic to its transpose. So by using Beck's theorem, I've shown that all of the row cycles are Hamiltonian, it now immediately follows that all the column cycles are Hamiltonian. So that's great, but maybe the thing is atomic. Maybe there are actually also Hamiltonian symbol cycles, but it turns out that's not the case. And to show it's not the case, I just need to find an element of ZP such that these three things are quadratic residues and those two things are not quadratic residues. And if I can find an X with these properties, then it will lead to a symbol cycle of length 3. So just on 3 symbols, I get a nice short symbol cycle. And it's easy to apply Weil's theorem and show that for all large P, there will be X that satisfy these properties, where large in this case means just 1600 or something. You can easily compute up to there and find there are always short symbol cycles. Well, nearly. Actually, for 19, it's actually atomic. So 19 in this case is an atomic square. 3 is as well, but that's sort of because 3 cycles don't stop it being atomic. So it's a small degenerate case, but 19 is somehow a bit different too. Anyway, we have an infinite family. Just happens that these two don't play the game. So that's the first part of the story. But about the time that Jack was doing this work, I got a message from my colleague Michael Kenyon, who asked me a completely unrelated question that I realized that we'd also just solved. So I want to tell you very briefly about that. But it's a problem in universal algebra, actually. So I need to tell you a little bit of algebra. So quasigroup is the algebraic notion that corresponds to Latin square. So it's like a group, but with weaker properties. All that we ask is, so we have a set binary operation. We just ask that there are unique solutions to equations 1 and 2. And that's basically saying that if you write down the operation table of this algebra, then you'll get a Latin square. So that's all that's saying. If your quasigroup has an identity element, then we say that it's a loop. And the other thing I need just for general background, an isotope of a quasigroup is, well, combinatorially, it means you permute the rows, you permute the columns, you permute the symbols, and then interpret that thing as another quasigroup. So that's the combinatorial definition of what isotopes are. You can define it algebraically. And the question that Michael asked me was about varieties. So a loop variety means I write down some identities, some equations, if you like, and I ask which loops satisfy these equations. And to make that a bit more concrete, if the identity that I chose to write down was the associative identity, then the loop variety that satisfied that would be the set of groups. Okay, something you can relate to. So, so you just write down identities like that and say which loops satisfy them. And what we want is actually the opposite of this. We want anti-associate varieties. They're ones that contain no groups. So you'll always have the group of order 1. You can't get rid of it. But assuming there are no other groups in your variety, we say it's anti-associative. It's isotopically closed if taking isotopes doesn't take you outside the variety. And in 1974, I think, Falconer asked a question, can you achieve anti-associative isotopically closed loop varieties which are non-trivial, meaning they contain more than just the trivial group? There's got to be something else in there. And this is a question which hadn't been solved in all that time. And we realized that we had just solved it. So how did we solve it? Well, you can look at the left and right multiplication map. So if you take any fixed element X of your quasigroup and look at what multiplying on the left does, that permutes the elements of your quasigroup. And you can play the same thing, play the same game on the right, multiplying on the right. That's a permutation of the quasigroup. And then if you take the composition of Ly with Lx inverse, that is exactly the permutation which is mapping row X to row Y, or vice versa. I never remember which, but it doesn't matter because they have the same cycle structure. So the row cycles in our Latin square correspond to the cycles of this permutation Ly composed with Lx inverse. And likewise, the column cycles correspond to Ry composed with Rx inverse. Now, if I insist that the pth power of all of the row cycles is the identity permutation, that's saying all of my row cycles had to have length p. And if I insist that I take the power which has all factors except p here for the column cycles and insist that's the identity, then I'm saying there better be no column cycles which have length p. And we can achieve this property. The square that I described doesn't have it because I had row and columns all Hamiltonian. If I take a conjugate and flip symbols with columns, then I can make sure that all of my row cycles are Hamiltonian, none of my column cycles are Hamiltonian, and then I will be satisfying these two identities. So actually, this identity, first identity corresponds to row Hamiltonian, and it's saying that every element of every loop isotope has left order dividing p. So in a quasi-group, you have a left order and a right order because it matters whether you're multiplying on the left or the right, but it's just the same concept as in group theory, order of an element. And here I'm saying that the right order should be co-prime to p. And I can achieve both of those things with the squares that I built, or with the conjugate of the square that I built. So in fact, there are infinitely many Falconer varieties. There's one for every prime that is 1 or 3 mod 8, except 19 or 3. So that was kind of nice. What have we still got to do? Well, we're a long way from solving Kotzig's conjecture, but that would be really nice. It'd be nice to know whether there are atomic Latin squares that aren't prime order. Here's a problem which we didn't solve, but I think is interesting. Can you, for given S and T, find Latin squares where every row cycle has length S and every column cycle has length T? And if so, for which S and T? And it would be lovely to use Beck's theorem to find other families of perfect one factorizations. We know these things are hard to find, but there should be lots of them. So this is a graph showing how many quadratic orthomorphisms. I hadn't told you what those are, but they're basically the same sort of construction that I gave you. How many of them produce perfect one factorizations? And it seems like there's lots, right? Slightly more for 3 mod 4 than 1 mod 4, because there are 1 orbit and 2 orbits. And anyway, there should be lots of these things, but there's not any structure to them that we can see. Now, I just want to finish with one observation. Last week, I was in Liechtenstein hiking to Falconer and discovered that I was walking along Route 66, which was lovely. Not the same Route 66 that Charlie had on his slide, but nevertheless, the views were amazing. I highly recommend it. And I just wanted to say to Doug, on your own personal Route 66, I hope you've also been enjoying the scenery. So, yeah.